everyone. This chapter is about wireless local area networks. So in this chapter, we'll first give a brief introduction of what is wireless LAN, and also we'll look at the basic technology used in wireless communication, that is the radio signal propagation. And then we'll also look at some of the related terms like what is radio band and also what is bandwidth, how are they measured. And then we'll look at something called spectrum transmission. And then we'll look at the more detailed operation of this 802.11 wireless local area network operation. And then we'll also look at the related transmission standards. And finally, we'll look at something called wireless mesh networking. Wireless LAN is part of the Layer 1 and Layer 2 standards. So if you look at the table here, you can see this 802.11 MAC layer standard. This part, then under that, then you have various different wireless protocol like Wi-Fi protocol like 802.11n and AC and so on. So all these actually belong to this 802.11 um area. So it actually spans through both layer 1 and layer 2. So this one is a chart comparing the Ethernet and the wireless LAN. So the Ethernet is the 802.3 working group and wireless is 802.11 working group. And then the major devices for Ethernet are switches. And then for wireless, there is the access points, the wireless access point. Although a lot of time we are saying we use the wireless router, as we mentioned before, this router actually is a combination of the router, a switch, and the access point. And the access point is actually the main feature that we need for the wireless. And then for the signal modulation, then for Ethernet is electrical signal or light. Basically, they are electromagnetic wave. And then for wireless, it's actually also the same. It's also electromagnetic wave that is transmitted through the air. But of course, in Ethernet, then the electrical signal are through the copper wire, and then the light wave is through the um, fiber optic. Yeah, so as we said, like copper wire and glass. And for wireless, then it's mainly through air, transmit and receive by the antennas. And the signal is standards are like 100 base T, 1000 base T, or 10 gig base T, SX, SR, LR, and so on. And for Wi-Fi, there is a 802.11b, A, G, and AC, and also AX, which is the latest standard, or what is also called Wi-Fi 6. The Ethernet network operates on OSI layer 1 and 2 and is actually the same for the wireless network. It's also on layer 1 and 2. And the dominant standards that we have seen, so for Ethernet is 802.3 and then for wireless is 802.11. So 802.11 is the current dominant wireless LAN technology. So it's standardized by the 802.11 working group, as we mentioned before. So it's basically what we call Wi-Fi nowadays. So there is a Wi-Fi Alliance, which is the industry association of 802.11 equipment manufacturers. So 802.11 standards actually have many options. And then the Wi-Fi Alliance actually selects some subsets of standards as what they call profiles. And then they also perform some interoperability testing on those profiles. And then only products that pass can display the Wi-Fi logo, like the one that we have here. So sometimes they also develop new standards. So nowadays a lot of network are kind of like what we call hybrid switched and wireless 802.11 network. So again, imagine that you are working at home, then you may be using your wireless notebook that will be connected to your wireless access point through the radio transmission through the air. And then this access point is connected to a switch or like a modem that you use again at home, right? Or just connect to the modem provided by your ISP through the copper wire, the UTP. Right. So that's what we call a hybrid network. Right. So you have a switch here, and then this part is the wireless. So and then they work very well together. Of course, as you said, a lot of time, this is not a simple access point. This basically would be a device that functions as a router, a switch, and an access point at the same time. Yeah, but then if you are looking at a larger area like the campus, then the access point is just the access point that is connected to the switch. So the LAN connection is needed to give clients access to servers and internet access routers on the wired LAN. Yeah, because if you only have the access point, then this access point does not have connection to the internet, right? So so that's why we will need to connect to a switch, and this switch will be connected to the router for the internet access, and they can also be connected to other devices within your organization. Now we'll talk about radio signal propagation. So as we briefly mentioned last time, electromagnetic wave actually travels like this. So there's a wavelength here, and then this one is the amplitude, and then frequency is the number of cycles per second. And normally radio transmission is described in terms of frequency. So typical data length frequencies are 500 megahertz to 10 gigahertz. So optical fiber transmission is also measured in terms of wavelength as we discussed last time. But then for Wi-Fi signal, because both of them actually are electromagnetic waves, so they are both measured by these characteristics. So to send the binary data over waves in radio transmission, the binary data streams must be modulated. That means they have to convert it from the digital signals to the electromagnetic wave. So there are three ways of modulation. So that is how we can encode this digital data into the electromagnetic waves. So they can be done by frequency, the amplitude, and also the phase. So there are three main ways of modulation. So if you do it in frequency, it's kind of like this. That means when you send the wave in low frequency, it can represent 0. When you send in high frequency, it means you have a shorter wavelength, then that's would represent 1. So that's what we call the frequency modulation. If I want to send the signal or the data 1011, then I just say it like this. Low frequency, and then sorry, this is high frequency, and then low frequency, and then high frequency, high frequency. Then it will be able to send 1011 as the wave. And for amplitude modulation, that means you try to send the wave in lower amplitude, then it will represent 0. Higher amplitude, then represent 1. If I want to send 1011, then it will be like this. High amplitude, low amplitude, high amplitude, high amplitude. Then we can also do phase modulation. Phase modulation, that means whether it's kind of like what we call in phase or out of phase. So if we are sending it like this, then we can call it in phase. Then something like this is 180 degrees out of phase. So the signal actually goes like this. So that means kind of the timing is different. So it's out of phase. So now if I want to send the signal 1011, then actually I can also say it like this. So this is in phase, out of phase, in phase, in phase, right? So then we can actually combine the three different ways of modulations together, and for each one of them we can also have different modifications that we can do to make it richer. So one way to do it is actually we have called this binary phase shift keying. So like if I just do the serial binary data. So that we want to send, so it's like this 100101. So what we can do is like we can do something like this. So this one is the um one, so with in phase, and this one you have the phase change, right? So this is our phase, and then this one again you change it back to in phase, and then out of phase, and then in phase. So that's what they call binary phase shift key. And then you can also do the quadrature phase shift keying. So that means instead of just doing two way of out of, it's kind of like one in phase and one is 180 degrees out of phase. Actually, you can also do different degrees of out of phase module signals. So for example, instead of having just 180 degrees, you can have four different phases like 45 degrees, 135 degrees, 255, 225 degrees, and 315 degrees. Then you can use these four different phases to represent more signals, right? So you have represent 2 bits like 0001, 10, and 11. So we have represent like this. So if it is like the signal is 00, so we represent, you send this wave like this. If it's 01, then this. If it is 10, then you send like this. Then 11, you send like this. Then that means with the same amount of wave, then now you can actually represent four different possible values instead of two. So you can represent 2 bits instead of one. So just like this. So this is the relationship between QAM, which is the quadrature amplitude modulation that we discussed in the previous class, and also the distance. So when you have use symbol like QPSK, that we say is 2 bits that you can send per symbol. And then normally because it's not so complicated, right? So you can travel a longer distance, right? The which can be like even 4,000 km, right? And then when you go for the QAM, as we mentioned, like 8 QAM, so we represent 8 different possible values. So that means you are sending 3 bits. Then the distance will be shorter. When you have 16 QAM 4 bits, that will be even shorter. 32 QAM, 64 QAM, then of course the distance will be even shorter because of these more symbols that you are more bits that you are trying to represent in the wave, then the chance of error will also be higher when you send it through a long distance. So that's why the distance will become shorter and shorter when you use higher QAM method. So now we'll talk about these antennas. So we have something called omnidirectional antenna. That means they will send signals in all directions. And then when you send in all directions, normally that means the signal will be weaker. So and there will be a rapid signal attenuation. That means it will become weaker and weaker. So the good thing is you don't need to point it at the receiver. So it's getting signal from all the angles, and then it's also sending out signal in all angles. And then the other type is the dish antenna. So dish antenna actually focuses signals in a narrow range, and signals can be sent over longer distance. So it's normally like this: you have a dish, right, and then the dish will basically sending the signal in one direction and also receiving signal from that direction. So of course we know like when you have this, you must point it correctly at the receiver. Otherwise, the signal will be very weak or even not receivable. So these are some example of these omnidirectional antennas, what we call the rubber duck, and then some patch and stitch, or some embedded antenna, or like some dome-shaped antenna. So just quick questions. What type of antenna do mobile phone use? Why? Actually, you can easily see from the figure, even the example here for the mobile phone, we are using omnidirectional antenna. The major reason is like when you use this, you do not know where your Wi-Fi access point is, right? Or even for cellular phone, it's the same case. You do not know where it is, so it's actually not practical for you to point at um, the wireless access point all the time. So that's why you will need to be able to send and receive signal in multiple directions. And again, this one is the omnidirectional antennas on phone. Like of course we know in the a lot of these older like Nokia or Motorola phone, you have an antenna that is visible like this, right? But nowadays, many of the newer phones, the antenna actually is just a small thing inside your phone, so it's usually small that you do not see it like this. Because of improved technology, now we can hide this inside the phone. So these are actually the when you take it out from the phone, they kind of look like this. So in the wired transmission in LAN that we talked about in the last chapter, the propagation effects can be controlled by respecting the core distance limits and also taking other installation precautions. So it's much better, much more reliable, and it's under your own control. However, radio propagation in Wi-Fi, usually we know, is very unreliable. It can be affected by many different factors, and the propagation effects in wireless networks are complex and difficult to implement. So there are five common wireless propagation problems, which we will talk about next. So the first problem is the what we call the electromagnetic interference. It's called EMI. So basically, it's unwanted power at the same frequency from other devices. So there are other people who are also using their Wi-Fi, right? So and then there are also actually other kind of things in the environment that will affect your electromagnetic wave, right? There are other electromagnetic waves that are in the air, like from all the sunlight and basically light um, from different sources, and also other magnetic field that can also somehow have some effect on your electromagnetic wave. But the most important one is actually the power at the same frequency from other devices that will have a lot of effect on your signals. So the second problem is what we call shadow zone or dead spots. So these are places where the signal cannot penetrate because of obstacles in the path. So they grow worse as frequency increases. So this comment is very popular. In this problem is very popular and common in Hong Kong because in a lot of Hong Kong apartments, we have many walls, right? And then when you lock yourself in the room, then you cannot get the Wi-Fi signal from the living room. Also, like within a campus, it's also the same. When you are inside a classroom, you cannot get the signal from the wireless point, access point outside the classroom, right? And also the problem is worse when the frequency is higher because when the frequency is higher, usually it's much more difficult for the wave to go through the wall. When the frequency is lower, it's easier. Yeah. Um, because the wavelength is longer. Normally that means it's easier to travel a long distance and also pass through the walls. But then for lower frequency, it's much more difficult. So that's why again, when you are using your wireless connection, and a lot of times the lower bandwidth like 2.4 gigahertz is better for going through a long distance and also going through the penetrating through the walls because of the lower frequency. Whereas the 5 gigahertz bandwidth is usually for very short distance where you can see the access point directly without um, turning any angles or going through any walls. So the third problem is what we call the signal strength attenuation. So basically the signal strength will spread out as the surface of a sphere like this, right? So when it goes out, the power of the signal becomes weaker and weaker. So the signal strength actually fall as 1 divided by r squared, where r is the radius. So that's what they call the inverse square law of attenuation. Um, so that means it will become weaker and weaker, um, exponentially because it's r squared, right? So if you double the distance, you only get 1/4 of the signal strength, right? So that's why it's not linear. The relationship is square. So the further we got away from the access point, um our signal will become again exponentially weaker. So the radio signal spread out in a sphere, as we said. So suppose S is the signal power, R is the range, or radius, right? So say if the signal power at 10 meters, so if you are 10 meters away from the access point, then the signal power is 9 milliwatts. Then how strong is it at 30 meters? So let's assume the signal at 30 meters is S2. So the original signal strength, signal power is S1. And then so we have R1 divided by R2 squared times this original signal, right? So then this one is like 9 milliwatt is the signal at 10 meters, and now it becomes smaller, so it becomes 10 divided by 30. As we said, we need to take the square. Yeah, so it's 1 divided by 3 square, so it become 1/9. So that means the new signal at 30 meters is only 1 milliwatt. So you increase the distance by 3 times, but then your signal power will drop by 9 times. So just a quick question, if the signal strength at 5 meters is 48 milliwatts, then how strong is it at 20 meters? So again, you can do the calculation. So because the distance has increased by 4 times, so the signal actually will decrease by 4 square times. So that means it will decrease by 16 times. So the new signal power will only become 3 milliwatts. So this one is the fourth problem of the wireless propagation. So this one is what we call the absorptive attenuation that will increase with frequency. So that means signal is absorbed by the air and water. Yeah. So when we talk about the um, inverse square law of attenuation, this one is really about the distance, it's not about the air and water. So even if you kind of send the signal in vacuum, for example, then it will still attenuate because it is basically becoming weaker when it travels. But then when you have air and water, it will also add to this effect, right? So that means you have some other media, air, water. Of course, if it's the wall, then it will be worse. But then even air and water will absorb some of your signal. So this is another type of attenuation. So just note that there are two types of attenuation. So one is the inverse square law attenuation, and this one is what we call absorptive attenuation. So just absorbed by air and water. So the fifth problem is what we call the multipath interference. So that means the direct and reflected signals may interfere and they may arrive at your device at the same time or at different times, right? Because for example, this one is the antenna from your access point. Then you have the direct signal going into your computer. Alright, so that one is the path we want. That's okay. But somehow actually they may go through different paths. So it may actually go to another path and it got reflected by the wall and then also received by your laptop at the end, then your laptop will be very confused, like which signal should be taken, which one is the correct one. So this one is what we call the multipath interference. Yeah, this one is actually the most serious propagation problem at wireless LAN frequencies. Yeah, because of the different signals, different paths, then we need to figure out which one is the correct one and which one should be discarded. And then you can have more than two paths, right? This diagram is only showing two paths, but you can actually have so many different possible multiple paths. So the receiver has to carefully figure out which one is the correct signal that is intended for me to receive. So if the two waves are out of phase, they will even negate each other, giving no signal, right? Because normally your wavelength should um your signal should go like this, but then you have a refractive wave that is 180 degrees out of phase, so they are completely out of phase. When that happens, actually they will cancel out each other, because that's kind of the property of this electromagnetic wave. When they are out of phase like this, they can cancel out each other. Then they will also cause a very important problem. That is again difficult to handle for your receiver. So that's why multi-path interference is one of the most important problem in wireless transmission. So this diagram just summarizes the five major problems that we talk about. So you have these electromagnetic interference, your shadow zone, inverse square law attenuation, absorptive attenuation, also the multipath interference. And also, as we mentioned, there are two forms of attenuation, and then also they grow worse at higher frequencies, like for the absorptive attenuation and also the shadow zone are worse at higher frequency. So that's why when as we mentioned, a lot of times 2.4 gigahertz is preferred, especially in Hong Kong, like apartments, right? Because um, of the shadow zone problem, that normally higher frequency can be used when you are closer, and then that will give you a higher speed. Next, we will talk about radio bands and bandwidth. The frequency spectrum is one of the very important topic in all these wireless services nowadays. The frequency spectrum is actually all the possible frequencies, say from 0 Hz to infinity. So broadly speaking, all the electromagnetic wave can have 0 to like infinity frequency. So then the frequency spectrum is divided into blocks of frequencies called service bands. So service bands are dedicated to individual services like broadcast televisions, radios, FM, AM, emergency services, GPS, like the global positioning services, cellular, telephone, and so on. So the basically different standard organizations and also different governments have kind of defined which spectrum, kind of which blocks of frequency should be used for which service. So these are called the service band. Each service band is divided into channels, and the signal is sent in a single channel. For instance, a television channel. When you have, say, in Hong Kong, you have the Pearl channel, that is a particular frequency given to that service given to that particular television program, right? So that's why we actually call it channel. So channel 1, channel 2, channel 3 on your television. And then when you listen to radio, then you also have like different frequencies like 88.1, 94.6. These are some of the common frequencies used by some of the specific um, radio channels in Hong Kong, right? So then signals sent in different channels do not interfere with one another, right? Because they are given their own frequency range, right? So they can use that little range and then they won't interfere because their frequencies are different, right? So that's kind of look like the service band. For example, this one is for TV, and then outside TV, then you can have different channels, and then maybe some channels are assigned to television company one, and then some channels are assigned to another television company. Then earlier we saw a signal propagating at a single frequency, so kind of a simple sine wave. But actually, a signal's power spreads over a range of frequencies. So the range of frequencies is called the signal's bandwidth. So it's actually kind of send a signal it is not traveling at a single frequency. So so it has lowest frequency and highest frequency. So we try to make sure this one is not too wide, right? When it's too wide, then it's taking too much bandwidth. So normally we just give it into a small bandwidth, such that we can send the signal in that bandwidth, but it will not interfere with the signal in another bandwidth. So it's not a fixed, very precise number, but it's a small range. So we call the bandwidth. So normally frequency is measured in hertz. So that's why, as we mentioned earlier, like 2.4 gigahertz and 5 gigahertz, these are the two frequencies used by the latest Wi-Fi standards. So then channel bandwidth is the highest frequency in a channel minus the lowest frequency. For example, in 88 megahertz to 88.2 megahertz channel has a bandwidth of 0.2 megahertz. So 0.2 megahertz, that means 200 kilohertz. So that's the bandwidth of this, for example, radio channel. That normally you tune to 88.1. That is the point where you should get the best signal. Right? So then, for example, how wide should the channel bandwidth be? So it's just a question here. So that's actually something that we need to decide. So the idea is that there is actually a direct relationship between your required transmission speed and the required channel bandwidth. So when you double the bandwidth, you can actually double the possible transmission speed. So you multiply that bandwidth by n, actually it makes possible n times the transmission speed, right? So that's why we actually want to set the channel bandwidth such that it's good enough for your transmission speed, but it's not too wide, because when it's too wide, although your speed will be faster, but that means you'll be interfering with other channel, or in other words, the number of available channels will become smaller. So broadband actually means wide radio channel bandwidth and therefore high speed, right? So that's why when you have, a lot of times you talk about broadband connection for your internet, that means your bandwidth is very very broad, it's not narrow, right? So nowadays popularly like fast system are called broadband system, even if they are not radio systems. So it's like for your network connection, many of them are actually wired, right? But still I think it is quite common that people call it broadband nowadays. So in Wi-Fi, as we said, there is the 2.4 gigahertz bandwidth service band, and also the 5 gigahertz service band. So basically, there are two bands that are assigned for Wi-Fi. So 2.4 gigahertz to 2.485 gigahertz. This one is normally referred to the 2.4 gigahertz service band. So the propagation characteristics are good. And then for 20 megahertz channels, then only 3 non-overlapping channels are possible, because for some of the standards in 802.11, then each channel is 20 megahertz. But then we look at this from 2.4 to 2.485, then you can actually only have this kind of non-overlapping channels, you only have 3 of them, like this. Like there are the channels 1, 6, and 11 in North American standard. So then you may question, like, there should be like 85 megahertz here, right? But why there are only 3 non-overlapping channels? Why not 4? The reason is that between the 2 channels, you actually also need to leave have some space there, otherwise they are too close, right? So kind of for the by the definition here like this, then they could only put 3 non-overlapping channels. So that's why in the early days, many of these like Wi-Fi's, actually even nowadays like this, if you are using the 2.4 gigahertz service band, like your channels are a lot of times overlapping with your neighbor's channels, right? So that's why the signals are not that good, can be affected very easily. So this co-channel interference between nearby access points transmitting in the same channel would of course degrade the performance. Except in very small networks, usually it's difficult or impossible to put nearby access points on completely non-overlapping channels. Right? So a lot of times they will be overlapping or even the same. So that's kind of one of the limitations of this 2.4 gigahertz. So there are some ways to try to deal with this channel interference. So this diagram is showing the example. Say I have different access points. Again, if you visit the university campus, you may see many access points on the campus. And then you actually can see like you have a different access point. We may actually try to use different channels. For example, like if access point A is using channel 1, then the nearby access point should use the channels that are non-overlapping. So we may be using channel 6 here for access point B and D, right? And then ideally, maybe we should use access point 11 here, right? But say, suppose we are also using channel 6 here instead of channel 11, then these two will have interference, right? And then say if access point F is using channel 11, point C is using channel 6, and this one is okay, but then there are also interference here, right? So normally it's actually quite difficult or impossible to make sure that all your nearby access points are on different non-overlapping channels. So the 5 gigahertz service band actually is better in this sense. So it has more bandwidth. So you can have between 11 and 24 non-overlapping 20 megahertz channels, right? So instead of 3, you can have like 11 and 24 non-overlapping channels, depending on how you set it up. So it makes it easy to have nearby access point operate on non-overlapping channels. Also, you increase your channel bandwidth in newer standards, that you can reduce the number of possible channels. That's at least the issue is here is like this, because as you said, when you double the channel bandwidth, you can double the speed, right? So when you make the channel wider, instead of 20 megahertz, you use 40 megahertz, then the speed will be higher. But then again, the chance of overlapping will also be higher. So some of the standards actually will increase the bandwidth, in order to increase the speed. But then when you do that, the number of possible channels will be smaller. But at least in the 5 gigahertz, you have this flexibility in the standard. Okay, so just two quick questions here. So what is the main advantage of the 2.4 gigahertz? Then also what is the main advantage of the 5 gigahertz operation? So as we said, some of the main advantage of 2.4 gigahertz is because of the lower frequency, actually the chance of the attenuation, and also for the absorptive attenuation, and also for the shadow zone will be lower. Yeah, because you can go through the wall more easily, so you can travel a longer distance. And then 5 gigahertz is for shorter distance, but then number of non-overlapping channel will actually be much higher. So that means you can use more channels without interference. So many of the late kind of the latest standards like AO2.11 AC and also A8, they actually both support many of the devices actually both support the dual bands. That means they will support both 2.4 gigahertz and 5 gigahertz. So that's why when you are buying a new router, a new access point, they may be saying they are dual bands. That means they support both service bands. So if two nearby radio hosts transmit in the same channel, then their signals will interfere. So that's why normally the government will have to kind of manage all these different radio bands. So most radio bands are what we call the licensed bands, in which hosts need a license to transmit like FM radio or television and so on. So in many countries it's actually illegal for you to operate your own TV station or radio in some what we call the licensed radio bands. But of course, there are some unlicensed bands that you may use, right? So the government usually limits the licenses to control the interference. So and also that will make sure that all the services like television, radio, and even some of the others like GPS and so on can be used without problems. And also in cellular telephone bands, only the central antennas are licensed, but they're not the mobile phones. Right. So again, it depends on um, kind of the actual law of the country, but that's usually the operation. So many of these bands are licensed, and then there are also some unlicensed bands that we'll talk about soon. So these unlicensed radio bands are field service bands that are set aside for unlicensed bands. So hosts in these service bands do not need to be licensed to be turned on or moved. Then that means anybody can operate anywhere. Then this will give some flexibility for some of the services that people can use. And normally these kind of services are not for broadcasting. They are more for like um closer distance communications. But of course again it depends on the exact law of that country. So AO2.11 Wi-Fi operates in the unlicensed radio bands. So as we said, one of the major reasons is basically these unlicensed means everyone can use easily. So you can set up your own access points or hosts, and then they can move freely. And also because they are not supposed to be traveling a long distance, right? Not for broadcasting like TV or radio. Then so the kind of chance of interference is lower. So that's why everyone can use it freely. So there is no legal recourse against interference from other nearby users. So if you are using Wi-Fi at your home and if someone use some devices that will interfere your Wi-Fi. Actually, normally there is again no particular. There may not be particular law to protect that, but again it depends. Right? Some countries actually are starting to do about that because so many people are using Wi-Fi. If you try to maliciously um, affect the operation of other people's Wi-Fi, then there may be some legal consequences. Right? um, So normally, like you should not cause unreasonable interference by transmitting at illegally high power. That should be something that is also kind of that we need to be careful, right? Because when you are operating something like this, you may actually affect your neighbors, affect other people using this. But again, as we know, some of the services actually use things like this. We say, especially we talk about army and sometimes some police, they will use this to interfere other people's Wi-Fi such that they cannot do Wi-Fi transmission um, at like in a certain area. In this subsection, we will talk about something called spectrum transmission. So spectrum transmission is mostly used to reduce propagation problem like multipath interference and other interference. So actually, you are required by law to use spectrum transmission in the 2.4 and 5 gigahertz band. So it's not used for security for in wireless LAN. It's mainly used to reduce those propagation and interference problems. So the idea is like this: like normally, say if the channel bandwidth required for signal speed is this, so in this diagram, you use the height of the box to indicate the bandwidth of the channel. Then the bandwidth that you assign is actually no wider than that required for the signal speed. So basically, we just use the same bandwidth without any buffer. So why do we not want to make radio channel bandwidth greater than the signal requires? Of course, like if we not make it bigger, that means we can have more channels. But normally when we do spectrum, we what we do is the channel bandwidth is actually much wider than required for the signal speed. So if the signal speed require this bandwidth, we will actually have a much wider bandwidth allocated to that channel. So you are wasting a lot of bandwidth in that sense, right? But actually this is necessary to avoid the propagation problem. So one technique used is the orthogonal frequency division multiplexing, so the OFDM. So basically what we do is a wide channel is divided into many subchannels, and subchannels are called the subcarrier, and information is sent redundantly. So if one subcarrier is lost, still no data is lost. So basically you send a part of frame like this, with the different subcarrier, right? Basically you send the same information redundantly, so that means you have the kind of more, you have the backup there. If one subcarrier is lost, you still get all your data. So now next we'll talk about the wireless LAN operation under 802.11. So as we have looked at before, a typical 802.11 Wi-Fi operation, you do it with a hybrid network like this. So the sender may put a packet for the destination host into an 802.11 frame like this. So if I want to send a packet, so I'll put it into an 802.11 frame. Remember, packet is like for the internet, like IP. I want to send it to a web server or send it to another computer on my network. So I first put it as a frame in my local network. So there's a local network between your notebook and the wireless access point. So that's a local network. So you send this frame through radio transmission. That means through your Wi-Fi signal to this wireless access point. And this frame, after arriving the access point, it actually has a different frame to travel over the Ethernet, right? This frame was only used for the wireless transmission. So what will happen here is that the access point will remove the packet from the frame. So it will take out the packet from the frame, and then it will discard the outer frame header. So it will take the packet, and then you will kind of put the packet into a 802.3 frame. So the packet is still the same, but there will be a new frame that is for Ethernet. Right, so that's why we have this from the 802.11 frame containing the packet. Once it arrives here at the access point, we take away the frame header, throw the frame header away, and then the packet will be put into a new frame that is for this single network. Remember, frame is for single network. Yeah, so that's why this packet will travel in the new frame in this local network. So that's the basics of the Wi-Fi operation. And then as we said, the access point encapsulates the packet in an AO2.3 frame and sends the frame onto the destination host via the Ethernet switches. And then the server removes the packet from the AO2.3 frame. So the frame header is thrown away, and then we just take the packet and then get the content of the packet. So in this case, the wide Ethernet network is called a distribution system. So some questions. Does the IP packet travel all the way to the destination host? The answer is yes, because it is still the same packet, but just with different frame. So you can again think of it like as a packet being put in different envelopes. Okay, so second question, does the AO2.11 frame travel all the way to the destination host? Why or why not? Now, of course, we know from the diagram in the previous slides, we know it's actually it does not travel all the way. It only travels up to the access point because actually it's not suitable for the Ethernet. So it's thrown away, and then we put the packet into AO2.3 frame in the Ethernet. So now we talk about something called the BSS, which is the basic service set. So it is actually a set of devices including an access point and the wireless host for this point. So then the SSID, service set ID, is the name of the network. For example, like ABC or whatever network that you give. Like when you set up your wireless router at home, you also give a network ID to the network, such that when you connect to the Wi-Fi, you use that name, right? So that's basically the SSID is the name of your Wi-Fi network. So that's called a basic service set. So and then we have something called the extended service set, the ESS. It's actually the collection of access points that all have the same SSID. Again, if you are on a university campus, you may have multiple access points, but these multiple access points actually share the same ID, right? You connect to the network, and then you can walk around on the campus, right, without having to connect to different Wi-Fi network every time. Although we know that when you walk to different places on the campus, you are actually connecting to the different wireless access point. The devices are different, but then you are still on the same network, right? The same campus network. So this one is called the extended service set. So a host can be handed off to a closer access point for service. Again, like when you are walking around on campus, say from the library to another building, then you will be handed off from the wireless access point at the library to the wireless access point on another building when you are getting closer to that building. So in wireless LAN, the ability to use handoffs is called roaming. So roaming requires that both access points belong to the same ESS. Right? So of course, they should be the same ESS with the same SSID. So otherwise, like you just have to reconnect to a new Wi-Fi network. So this one is actually covered by AO2.11R. Another issue with the wireless access point is channel sharing, because we know one wireless access point actually only operate in one chosen channel at a time, right? So when you have multiple people using the same access point, right? So you have laptop, phone using the same access point at the same time, there will be a collision if they transmit data at the same time, right? So the signals will collide and then become unreadable because they are in the same channel. So that's why there is actually some protocol to cover what should do what should be done when the multiple devices are using the same access point. So it's actually the media access control. So where the word MAC comes from. So the MAC methods actually cover when devices transmit so that only one device transmit at one time. So for example, when someone is transmitting, then the other devices must wait. So that's why when more people, more devices are using the same access point, the speed will become slower. So there is a method called the CSMACA plus ACK. So it's a very long name, but basically it stands for Carrier Sense Multiple Access with Collision Avoidance and Acknowledgement. So it's actually mandatory for 802.11 Wi-Fi operation. And then there are of course like different versions of this for different versions of Wi-Fi. So basically what they do is carrier sensing. So what is this is the sender will listen for traffic, so it will sense who is actually using it. So it's carrier sensing. So if another device is transmitting, then you will wait. Then this control access by multiple devices that must not transmit simultaneously. So everyone before transmitting, you will have to sense. You have to see whether there is traffic. And then there is the CA part, the collision avoidance. So when the current sender stops, then two or more waiting devices may immediately want to transmit, right? So I'm listening, but then there is no traffic now, then we want to transmit now, right? Because we all think we are in the queue. So this will also cause a collision. So based on that, so the solution is the devices must wait a randomized amount of time before sending. So this usually will avoid collision, but it is inefficient because you will waste the waiting time, right? But so that's one method of doing this. So it's the CA. And then we also have the acknowledgement and reliability. So what happens is when there is the acknowledgement here, the receiver will immediately send back an acknowledgement. So as you said, the collision avoidance will have some random delay for other devices. They will guarantee that there will be enough time for an immediate acknowledgement. So if the sender does not receive the acknowledgement, then you will retransmit using the CSMA. So then CSMA CA plus ACK, then it will be a reliable protocol. So we said when it's a reliable protocol, so that means it will have acknowledgement. So reliable protocols usually are rare in wired networks, right? Because when it's wired, it's kind of already quite reliable physically. But then for wireless network, because the radio transmission is quite unreliable, so normally it's good to have the acknowledgement. So that's why a lot of these 802.11 standards, they have this CSMA CA plus the ACK. So as we said, there is a lot of waiting time with this method, so there is some inefficiency there. So there is also another method, so that is called the RTS CTS. So basically, the host that wishes to transmit may send a request to send the RTS message. So I want to send something, so I will tell the access point, and then the access point also when it's okay, when no one is sending things, then you will broadcast a clear to send CTS message. So then when the CTS is being sent, then host A may transmit freely, and then other hosts must wait while host A transmit, because other hosts did not send the RTS, so they must wait. So host A is the one who sent the RTS, so host A can transmit. So as we said, CSMA-CA is mandatory, is the default method. It's more efficient than RTS-CTS, and then RTS-CTS is usually optional. It's actually good if two or more client stations cannot hear each other, because if the two clients are on the two sides of the wireless access point, then they are too far away from each other, then they cannot listen to the traffic of each other, then the CSMA CA may not work, because the clients cannot sense each other, right? They cannot do the carrier sensing. So the RTS CTS will help. then this will also stop them from transmitting at the same time. So now we will look at different 802.11 transmission standards. So the earliest standards in 1999 is 802.11b. So it's only for 11 megabit per second. So it's not very fast if we talk about today's standards. So it's in the 2.4 gigahertz band. So this one is kind of like the first standard, and the second one is 802.11a. So it's interesting that so the B first and then A, and then but actually they are around the same time. So this one is the OFDM that we briefly mentioned earlier, also in 1999. So this one is for the 5 gigahertz frequency band. So it used 20 megahertz channels, just like what we do in some of the later Wi-Fi standards. So this one is faster; it can go up to 54 megabit per second. And then there is the G standard. So it's actually also quite old. If you look at now, it actually is proposed in 2003. So it's based on OFDM. So it's in the 2.4 gigahertz frequency band. So then it also has 20 megahertz channels and also up to 54 megabit per second. So this one actually has been quite popular in the early 2000s. And then later on, then there is the N standard, also based on OFDM, and this one is dual band, so it can work on both 2.4 and 5 gigahertz frequency bands. So they use the 40 megahertz channels, but can also drop back to 20 megahertz, especially for the 2.4 gigahertz band because it's smaller. Right? So this one is much faster. It can go up to 600 megabit per second, and it also have the MIMO. So that we will talk about later. And then 2013, then they have the AC standard. So it's the 5 gigahertz frequency band only. But later on, there is also the dual band. So the improved version. So again, at the 5 gigahertz frequency, then they have the larger bands, larger channels. And this one have the MIMO, so it's an improved MIMO, right? So MIMO. So again, we will talk about exactly what it is later. So it's using 256 QAM, so which is much better than 64 QAM in the earlier versions. So we talk about QAM in some earlier slides about how we do the modulation. So it can also transmit up to have up to 8 spatial streams and also up to 6 gigabit per second. So in theory. And then this one is the latest standard, like this the AX standard, which is also called the Wi-Fi 6, because they find that people actually get very confused when you have B, A, G, N, A, C. So now they want to call it like Wi-Fi 1, 2, 3, 4, 5, and this one will be kind of officially called Wi-Fi 6. So that is kind of out at the end of last year, and now I think this year we are seeing many devices that are having this um basically running Wi-Fi 6 in year 2020 now. So it can also support dual band, also different width of channels, and then it's also running MIMO as we said, and then it has better better modulation up to 1024 QAM and also up to 11 gigabit per second. So this is the latest standard nowadays. So this is a table comparing the different Wi-Fi standards except for like B. So again, people could call it like Wi-Fi 2, 3, 4, 5, and 6. But in the past, people did not really use like Wi-Fi 2, 3, 4. So but they are coming up to this one AX, then the Wi-Fi Alliance, and it's better to market it calling it Wi-Fi 6 instead of a more technical name like NAC and AX. This table compares the number of channels and also the channel width in the major Wi-Fi standards. So it's only looking at the 5 gigahertz band in the USA. So for A, there is 20 to 25 channels, and for G is mainly just using the lower frequency band. And then for N, then actually there are two choices. Like if you go for channel width of 20 megahertz, then you can have more channel, right? But then if you have a wider channel, then you have fewer. So actually it's the same for the other standards. If you go for wider channel, and of course for each channel the speed will be higher, like 80 megahertz or even 160 megahertz. Then of course 160 megahertz the speed will be much higher, but then the number of channels will be limited. And for Wi-Fi 6 is also similar, like so you can also have this kind of channels, but also at the same time there are channels also in the 2.4 gigahertz band. So this one is the MIMO that we talked about earlier. So what exactly it is? So an access point actually transmit two signals in the same channel, right? That's something possible. So you can, like when you have two antennas, you can actually send one signal from antenna A and then one from the antenna B, right? So an antenna A will be sending like this, right? And antenna B will be sending like this, and the wireless host then will also be receiving using the different antennas, right? So if there are multiple antennas, so this is what is called the spatial streams. So the two signals arrive at different times at the two receiving antennas, right? Because this one the path is shorter, right? Spatial stream here, the upper one, the path is shorter, and this one is a little bit longer, right? So they will arrive at the antenna at a slightly different times. And the time differences actually allow them to be separated and understood. So that's why we can do this MIMO, which actually stand for multi-input, multi-output. So there are two major benefits. So the MIMO will bring higher speed because it can send more information in one channel. It also brings longer propagation distances because of some technical reasons, but we are not going into a detail. But basically, it can propagate longer. So these are the two major benefits of the MIMO. So it has been included in some early versions. It has been included starting from some early versions of Wi-Fi. And then we can also have like beamforming. So beamforming actually allows an access point to focus its transmission and reception. So this is access point with beamforming. That means instead of just sending all the signals to all the different laptops, I actually can try to focus on kind of a beam that is focusing my communication, my signals with one host. So that will actually make my transmission better. So and then this one is the new one that is in, I think it's in AC and AA. It's called MUMIMO. So it's a funny name, but basically it's from like multi-user, multi-input, multi-output. So it actually allows two wireless hosts to transmit at the same time, as long as kind of the beam is different. So you can actually sense where the signal is coming from, like based on the direction. Then actually we will know they are from the different hosts. So again, when you do this, then you can improve your signals um, strength actually, and can also improve the transmission speed. So it was defined in AO 2.11n, but then at that time it was not developed to a usable degree. However, with AC and AX, beamforming and multi-user MIMO, the MIMO actually are intrinsic parts of the system already. So they are well defined, they are included in the specification. So now this one is actually one of the major thing that kind of major feature that improve the speed in and the performance of AC and AX. So this one is a table showing some of the again compare the different Wi-Fi standards in terms of whether they are MIMO, the maximum spatial streams, and whether they support MIMO. Right, so as we said, earlier version does not have the MIMO. This one has, but it's not really working very well. But the AC and AX they have MIMO and also MIMO. And then spatial streams was kind of proposed in N, so there were four, and then for AC and AX there can be a maximum of 8 spatial streams. So this is a table again comparing the different standards. So going from A, G, N, and AC, right? But like as you said, like AC and AX we don't have AX here, but AC and AX in general, like they can be dual band actually. So actually it's we are saying like 5 gigahertz actually is not very suitable for a lot of Hong Kong apartments, Hong Kong environment because a lot of walls. But then they are dual band, so you can also support this 2.4 gigahertz. Right. So and then yeah, I think we have talked about most of this, the channel bandwidth, number of non-overlapping channels that you may use, like based on the US standard, and whether they support MIMO, number of spatial stream, MIMO and beamforming, and also the rated speeds. So for A and G, then the speed is supposed to be 54 megabit per second, and the N will be higher, and the AC is much higher, and of course AX is even better. Alright, then of course we note for rated speed versus the throughput, they are different. Like we talked about in earlier chapter, rated speed is a speed that the standard specifies, but you may not always achieve that maximum speed. Then throughput is the speed that is actually delivered. So total throughput usually is substantially lower than the rated speed, sometimes even 50% lower or even more. That's again because of wireless. Transmission is kind of more unstable. If we talk about wired transmission, then the throughput usually will be higher. Still, you are not reaching the rated speed, but it will be closer. But then for wireless, the difference can be very large. And then of course there is also a difference between the aggregate versus the individual throughput. Right? Access point throughput is the aggregate throughput for all devices transmitting and receiving. So if you have 10 devices using the same access point at the same time, then of course that speed will be shared by the 10 people, the 10 devices. So the capacity is shared by all stations currently sending and receiving. So of course, like if your mobile phone at the time is not doing any data transmission, then the speed will be used by, like for example, your laptop that is using the transmission, right? But then if they are all sending and receiving at the same time, then they will be shared. Then of course, like when you have many users, the individual throughput can be much lower than your aggregate throughput. So also as we know, as distance from the access point increase, the signals will get weaker. Then of course, then your speed will also decrease, right? So that's because wireless hosts must use slower but more reliable bit encoding methods. So that means instead of doing a lot of complicated modulation, you will use the easier one, right? So we will send fewer bits per clock cycle. So that's why if you are further away, it will be slower. Of course, when it is more unreliable, then there may be lost signals. Then you have to or lost data. Then you might have to resend again, right? So that's why when you are further away, that will become slower. So of course, this will reduce your individual throughput for your devices. So of course, in Wi-Fi, one of the good thing is most of the Wi-Fi devices nowadays, they have backward compatibility. That means the devices built for newer standards are still implementing the older standards. So this allows older and newer devices to communicate. So that means, for example, if you buy a new router at home, like that is running Wi-Fi 6, then even if your computer, your iPad, they are running like only 802.11n or 802.11 even G, right? They can still talk to the wireless access point without problem. So that's backward compatibility of the wireless router. And then on the other hand, like when you are using a mobile phone that is running Wi-Fi 6, right? But then you can also connect to a wireless access point that is running older version of the Wi-Fi is running 802.11n, right? So even if your router is old or the phone is old, normally they are both having the backward compatibility, right? You can work very easy no matter you are using new or old standards. So that's one of the very good thing about these network standards. I think most of the products support this backward compatibility. So just a quick example of backward compatibility. Suppose you have a new product 802.11 AC in the 5 gigahertz band. and the old product is 802.11n in the 2.4 gigahertz band. Then the new product, in this case the AC product, can drop back to a standard that the older product can use. So that means if you buy a Wi-Fi 6 wireless access point, actually it has all the standard. It knows how to do Wi-Fi 1, that means using BAG. It knows how to do NAC and so on. So it knows everything. So it can drop back to the standard. Any earlier Wi-Fi standard, normally they are compatible. So of course, in this case, it will use the older standard that is understood by both devices. So in this case, the two devices will be using 802.11n standard in the 2.4 gigahertz band. Now, of course, the speed will only be based on the speed of 802.11n. It will not be able to get the AC speed. So finally, we will talk about wireless mesh networking. So the idea of mesh networking is um, the frames are forwarded by access point and wireless hosts. So that means, for example, you may have two wireless hosts here, and then they are not connected by wire. So they are wireless. So basically, this host can pass the data to A through um, Wi-Fi, and then A can also pass to B, B can also pass to C, E can pass to B. So that means without the wired connection, like what we looked at in the hybrid network earlier, then you can also set up your mesh network like this. So normally, like you may not exactly have something like this, but one example of this mesh networking, wireless mesh networking, is actually the Google Wi-Fi. So some of you might have heard of it or might use it before. So basically the idea is like this. So they are actually running it on mesh. So when you have some, so when you use Google Wi-Fi, normally you may have the two wireless access point, right? And the two of them actually will also communicate using this kind of mesh network.